Okay, in this video, we're going to talk about the sample StatDisk assignment number 4. This should assist you with completing the actual StatDisk assignment number 4 found in my math lab. So we go ahead and get started with the sample problem number 1. And it says here a simple random sample of front seat occupants involved in car crashes is obtained. Among 2,825 occupants not wearing seatbelts, 31 were killed. Among 7,697 occupants wearing seatbelts, 19 were killed. Use a 0.05 significance level to test the claim that seatbelts are effective in reducing fatalities. And here we're going to complete parts A, B, and C below. One, we're going to test the claim using a hypothesis test. Part B, test the claim by constructing an appropriate confidence interval. And part C, what do the results suggest about the effectiveness of seatbelts? Okay, so here we can do this in StatDisk. Now notice we're dealing with two different proportions. One for occupants wearing seatbelts and the other will be for occupants not wearing seatbelts. Okay, so now let's go to StatDisk. Okay, and pretty much you just go ahead and log into StatDisk as you normally do. If you, of course, haven't, make sure you register for StatDisk. All right, now let's go to analysis first. Then we're going to go to hypothesis testing because that's what we're doing. We're testing a claim. So that means we're doing the hypothesis testing. Click on that. Now we're dealing with two samples for a proportion because you're given the number of occupants and how many were not wearing seatbelt, and then the number of occupants and the number who were killed wearing the seatbelt. Okay, so we want proportion two samples. This screen should pop up. Now let's think about this for a moment here. We're going to test the claim using a hypothesis, and we want to consider the first sample to be the sample of occupants not wearing seatbelts, and the second sample to be the sample of occupants wearing seatbelts. Okay, so P1 would be the first sample of occupants wearing seatbelts. Not wearing seatbelts, but P2 would be the sample of occupants that wore seatbelts. Okay. And the claim was that seatbelts are effective in reducing fatalities. So in this case, if P1 is going to be first, and then P2 is going to be second, think of this. P1 is the number of occupants not wearing seatbelts. That has to be greater than, in this case, because the fatality for those who are not wearing seatbelts has to be greater than those who were wearing seatbelts. So in our alternative hypothesis, we need to select greater than. Proportion 1 will be, population proportion 1 is greater than the population proportion 2. Okay, it's just the way the problem is worded and the directions that they give you, because they want you to consider the first sample to be those occupants not wearing the seatbelt, and the second sample will be those who were wearing the seatbelts. P1 not wearing seatbelt, P2 wearing the seatbelt. So anybody not wearing a seatbelt will have a greater fatality rate than the ones wearing the seatbelt. Okay, so that's why we chose P1. That's why we chose population 1 greater than population 2. All right, significance level in that problem, they do tell you to use, I'll go back to it, a 0.05 significance level. So that's already given to you in the problem. If another significance level is there, you just have to type in 0.05. Now, sample 1 will be the number, will be dealing with those who are not wearing seatbelts. There were 2,825 occupants not wearing a seatbelt. So we type in the 2,825 in that box. And the number that were killed for not wearing a seatbelt, 31. We type that in. And that's going to come from here, as it does say, among 2,825 occupants not wearing seatbelts, 31 were killed. And then for sample 2 would be this, 7,697 occupants wearing seatbelts, only 19 were killed. So when we go down to sample 2, we type in the 7,697, and then for the number of successes will be 19. And that's all there is to it, okay? Next, we'll click on evaluate, okay? So here that alternative hypothesis was that P1 is greater than P2. In the assignment for StatDisk number 4, you'll have to choose which appropriate alternative, null and alternative hypotheses for this particular problem. And this will be the alternative hypothesis where P1 is greater than P2. All right, also they want the Z test statistic. That's what Z is. This is going to be this number. To 2 decimal places, it will be approximately 5.62. Also, they want the p-value. This will be your p-value, 0.000. Now you compare the p-value with your level of significance, and if your p-value is less than your significance level, you reject the null hypothesis. In this case, 0.000 is less than 0.05. So we can easily reject the null hypothesis and say that there is sufficient evidence to support the claim that the fatality rate is higher for those not wearing seatbelts. Okay, so that will be part A. Now, part B is to test the claim by constructing an appropriate confidence interval. Well, take a look at this. When we did our hypothesis test for a proportion with 2 samples, notice we got our confidence interval. And this right here is a 90% confidence interval, okay? So that means, and in this case here, they want this, I think, to 3 decimal places. So the lower limit would be 0.005 and the upper limit will be 0.012. Okay, yeah. So that's your confidence interval right here. That's what they want. All right, now what can we conclude based on that confidence interval? Well, if you look at this, the confidence interval limits do not include 0. They're both positive numbers, so they don't include 0 in here. So that means we can say that the 2 fatality rates are not equal because the confidence interval limits include only positive numbers, as you can see in this case. And it does appear that the fatality rate is higher than those not wearing seatbelts, okay? So this is another way to reject the null hypothesis. Here, these 2 do not include 0, so that means we can reject the null hypothesis. If the confidence interval limits do include 0 in it, then we would fail to reject the null hypothesis. And then the last part, part C, what do the results suggest about the effectiveness of seatbelts? Well, the use of seatbelts is associated with lower fatality rates than not using seatbelts, based on those results that we got from StatDisk. Okay, problem number 2, StatDisk problem, sample problem number 2, I should say. It's this: a study was done on proctored and non-proctored tests. The results are shown in the table. Assume that the 2 samples are independent, simple, random samples selected from normally distributed populations, and do not assume that the population standard deviations are equal. And here I want to complete parts A and B below. So here's the table that we're going to be dealing with. And in part A, I want to use a 0.01 significance level to test a claim that students taking non-proctored tests get a higher mean score than those taking proctored tests. All right, so now let's think about this right here. If non-proctor tests are going to be higher than the proctor tests, then that means that these proctor tests will have to be lower than the non-proctor tests. That's what this means. Okay, so students taking a non-proctor test get a higher mean score than those taking a proctor test. That means that the proctor test has to be lower than the non-proctor test. So when we select our null and alternative hypothesis, of course, the null will have to have the equal sign no matter what. If you recall, null always has the equal to sign. But for the alternative, it would have to be less than. Because we'll let me1 be the proctor test and me2 be the non-proctor test. So non-proctored is going to be greater than the proctored. That means going this way, the proctored will have to be less than your non-proctored test. All right, so now let's go back to StatDisk. All right, now let's go to analysis, hypothesis testing. Now we're dealing with two means, and we're dealing with two independent samples as indicated in the problem. So we need to select the one that says mean two independent samples. All right, and based on what I just mentioned in that problem there, the non-proctored will have to be is greater than, that means your proctored will have to be less than. So in your alternative hypothesis, you must select population mean 1 is less than population mean 2, based on that. All right, significance level is this. Let's go back to that. It says 0.01. We're using a 0.01 significance level, so we need to change our significance level from 0.05 to 0.01. Okay, tab down to the sample size for N1. That's going to be for the proctored test. That's going to be, I'll go back to it. That's just right here. This first column for the proctored test, that goes in sample 1. Sample size 1, or sample 1. Your sample size for N1 will be 31, as indicated there. Sample mean was 74.19. And then tab down to the sample standard deviation for the first would be 11.24. The population standard deviation is always going to be blank because we never know what that population standard deviation is going to be. All right, now go to sample 2. We enter the summary statistics for sample 2, which is a non-proctored test. Sample size 2 was 30. Sample 2 mean was 88.38. And then sample 2 standard deviation was 21.43. And again, the population standard deviation is left blank. Now, for method of analysis, we always select unequal variances because we're told in that problem that we are not to assume that the population standard deviations are equal. So we always select that unequal variances, no pool recommended. That's recommended there. All right, and then we're going to click evaluate. All right, now in this problem here, they're going to ask for the test statistic, which is this. To 2 decimal places, it'll be -3.22. And then they may ask for the p-value, which is right here, 0.001, rounded to 3 decimal places. And then we want to decide whether to reject the null or fail to reject the null. Again, the decision rule says if your p-value is less than your level of significance, you can reject the null hypothesis. In this case, our p-value of 0.001 is less than 0.01. So that means we're going to reject the null hypothesis. And if we reject the null hypothesis, that's going to mean that there is sufficient evidence to support the claim that the students taking non-proctored tests get a mean a higher mean score than those taking the proctored test. Okay. Now, let's look at part B, construct a confidence interval suitable for testing the claim that students taking non-proctored tests get a higher mean score than those taking the proctored test. Okay. Notice at the very bottom of this output, you'll see your confidence interval, which is this. And if we were to round those limits to 2 decimal places, it would be negative 24.82 to negative 3.56. That would be your confidence interval. Okay. And does that confidence interval support the conclusion of the test? In this case, it does. And the reason for that is that our confidence interval limits only contain negative numbers. Okay, it does not contain 0. So we can reject the null hypothesis here. Now, let's say that the lower limit was negative and the upper limit was positive. Then that would mean we can fail to reject the null hypothesis because notice you will have a 0 in between your confidence interval limits, one being negative and the other one being positive. Okay, so that's number 2. All right, number 3. Listed below are the numbers of words spoken in a day by each member of 8 different randomly selected couples. And here are one of the complete parts A and B below. And here you see the table for male and female. And then in part A, it says use a 0.01 significance level to test the claim that among couples, males speak fewer words in a day than females. And part B, just construct a confidence interval that could be used to test the claim for the hypothesis test described in part A. What feature of the confidence interval leads to the same conclusion reached in part A? Okay, now this can be done on StatDisk. So let's go to StatDisk here. And I want to mention this right here. When we go to analysis, hypothesis testing, notice that we have randomly selected couples. So that tells me I have paired data. So under hypothesis testing, we're going to select the one that says mean matched pairs. Okay. So here we're dealing with the average, we're dealing with the mean. So that means we're looking at mean matched pairs. So that's the one we want to select under hypothesis testing. Okay. Now we're testing the claim that among couples, males speak fewer words in a day than females. So under hypothesis testing, we want to select not equal to, not equal to, less than 0, because we're saying males speak fewer words in a day than females. So it's got to be less than 0. Our significance level in that problem was 0.01, so that means I'm going to do 0.01. Now, this says data, and we are given raw data. So that means I need to go here to sample editor, toggle sample editor, which is this right here, and enter those data values in here. In column 1, I'm going to enter the number for male, the data values for male, and in column 2, I'm going to enter the data values for female. So for male, I'll start here with 15,099, type that in, and then 25,441, enter, 1388, enter, 7685, then enter, 19,459, enter, 15,615, enter, 14,519, and then enter, then 25,070, and then enter. Okay. So here I'm just entering the data values for the male row. Okay. And then for female, I'll enter that in column 2. So these are the numbers there, 24,768, and then 13,616, 18,267, then 17,311, 12,862, then 17,422, 15,972, and then 18,012, and then enter. And you want to make sure that the number of data values in the first column is equal to the number of data values that you have in column 2. And make sure that you enter your data values correctly. Okay. All right, so now I've already got this part right here, so I can go ahead and select which columns of data I want to compare. I'm comparing column number 1 to column number 2. So on the left side, I select column number 1. Then on the right side here, I'm going to select column number 2. Okay. And then finally, we're going to click on evaluate. Okay. Now let me do this here. And in this case here, this is our outcome right here. The t-test statistic is what they want. This will be negative 0.50 if I round this off to 2 decimal places. Negative 2.5, negative 0.50 if I round that off to 2 decimal places. They also want the p-value. Well, the p-value is going to be right here, 0.31666 or 0.317. That's your p-value. Now we decide whether to reject the null or fail to reject the null hypothesis. Again, if that p-value is less than your level of significance, you reject the null hypothesis. In this case, it's not. 0.317 is greater than 0.01, so we need to fail to reject the null hypothesis. Okay, so that means that there's not sufficient evidence to support the claim that males speak fewer words in a day than females. Okay, so that would be the answer to part A. And now part B is to construct a confidence interval that could be used for the hypothesis test described in part A. What feature of the confidence interval leads to the same conclusion reached in part A? Well, in this case, here's our confidence interval right down here. And to the nearest whole number, it'll be from negative 12,231 to positive 8,743. Notice in this case that I have a negative on the left side and a positive value on the right side. That means 0 is included in this confidence interval. So that would lead me to fail to reject the null hypothesis, okay? Because the confidence interval only contains, it does contain 0. So that means we can fail to reject the null hypothesis, okay? That's the difference there. All right, and finally, problem number 4. This deals with a correlation and regression problem here. Because here we're going to find the regression equation, letting the first variable be the predictor variable or the X variable, using the listed actor, actress, actor ages in various years. Find the best predicted age of the best actor winner, given that the age of the best actress winner that year was 58 years old. Is the result within 5 years of the actual best actor winner whose age is 45 years. Okay, and this is our data set right here. We're going to have to enter this data set in first. Okay, so now let's go to StatDisk. I'm going to click on Toggle Sample Editor and then clear this out. So in the first column would be the best actress age. That'll be the age for the best actress. I'll enter that in first because we're letting the first variable be the predictive variable. So best actress would be my X variable or the predictive variable. So I enter those data values in like 29, 28, 30, 58, 31, 33, 45, 29, 60, 22, 42, and 51. Then the next column, column 2, will be for the best actor ages. So it would be 44, 37, another 37, 45, 48, 48 again, 59, 50, 37, 55, 43, and 35. Okay. Now we're doing a correlation and regression. Okay. Because they want the regression, the equation of the regression line. So I'm going to go to analysis first and then go to correlation and regression. Click on that. The significance level, I'm going to leave that as 0.05 because I don't believe they mentioned a significance level in that problem, as you can see here. So I'm going to leave it at 0.05. The X column that I'm going to select will be column 1, which was the best actress's age. The Y column would be column number 2, the best actor ages. And then I'm going to click on evaluate. All right, so now the regression results are right here. Now you need to understand that the y-intercept would be b sub 0 and the slope will be b1. And this is your regression equation, y equal b0 plus b1x. So that equation would be y is equal to, you'll substitute b0 with that 51.4, because they say round the y-intercept to 1 decimal place. So it'll be 51.4 for the y-intercept, and then plus, and then to 3 decimal places for your slope, negative 0.173x. Okay. Okay, because if you remember back in algebra, when you're dealing with graph and linear equations, pretty much your x is, the number in front of the x will be your slope. The number added to or subtracted from that linear term is going to be your y-intercept. So this b sub 0, this is your b sub 0, 51.4017, or 51.4. That would be your y-intercept. This would be your slope, negative 0.173x. Okay. Now, to find the best predicted age of the actor, of the best actor winner, given that the age of the best actress winner that year is 58 years. Now, here comes the tricky part right here. You have to look at your p-value to see whether or not there's a linear correlation. You're comparing the p-value with your level of significance. If your p-value is less than your level of significance, then that means we can reject the null and say that there is sufficient evidence of a linear correlation. But in this case, our p-value of 0.360 is bigger than 0.05. So that means we need to fail to reject the null. And that will mean that there is not sufficient evidence to conclude that there is a linear correlation between the ages of best actresses and best actor. And when there is no linear correlation, that means the best predicted value is going to be the average of whatever y is, or the average of the second column in this data that we just did. Okay. Now, this is the case right here where we have to fail to reject the null. And this is the case where we're going to need to find the average of the best actor. So I need to go back to this sample editor to go back to the sample data in this case, which is this right here. Now I need to find the average of column number 2, because that's the column for best actor. Here I'm going to go to data. I'm going to go to explore data, descriptive statistics, click on that. And the column that I want to evaluate would be column number 2. That's for best actor, as it was placed in column 2. Click on evaluate, And here is the mean right here. Let's say to 1 decimal place. It will be, it says 44.8333. To 1 decimal place to the nearest whole number will be 45. So the best predicted age of the best actor winner, given that the age of the best actress winner that year is 58 years, is 45 years old. And also they asked the question, is the result within 5 years of the best actor winner whose age was 45 years? And in this case here, to answer that particular question, the answer there would be, it would be yes, that the predicted age is 5 years or less from the actual winner's age. Okay. Now, I would admit that some of these questions in this video can be a little bit tricky, but if you think about this, think about these problems for a moment, you should be able to answer them correctly. Okay. So hopefully this video will assist you with completing the actual StatDisk assignment number 4 in my math lab. But do feel free to email me or call me if you have any questions about anything in this video or in the StatDisk assignment. I'm glad to help.